So good evening, ladies and gentlemen. Thank you again for sticking around. So now we are going to look at this topic called IP addressing. In the previous chapter, we saw how data is formatted at the data link layer before being forwarded to the destination. Now here we are going to the network layer, also known as layer 3. That is where IP addressing really happens. So I'll read the foreword. The Internet Protocol is designed to provide a means for inter-network communication that is not supported by lower layer protocols such as Ethernet. Inter-network communication is this. For example, if I wanted to write a letter to someone in MMU, I'll simply write the letter and hand it over to them. So we are in the same network. But if I want to send to Kabianga University, or to Kwale, or to Taita, that is a different network, so I have to go through Posta. So that is what IP really enables us to do, inter-network communication. So the implementation of logical IP addressing enables the Internet Protocol to be employed by other protocols for the forwarding of data in the form of packets between networks. So data at the network layer, we call it packets, the PDU, the protocol data unit. So strong knowledge of IP addressing must be attained for effective network design, along with clear familiarity of the protocol behavior to support a clear understanding of the implementation of IP as a routed protocol. By the end of this chapter, you should be able to, Bethwell, you can just enable your mic and help us read these objectives.
Be able to the fields and characteristics contained within IP to distinguish between public, private, and special IP address ranges. 3. Successfully implement VLSM addressing. And 4. Explain the function of an IP gateway.
Exactly. Okay. So we're going to learn about all those things here. So, okay, I'm trying to find my window here so that I can annotate. Are you able to still see my screen?
Yes.
Okay, thank you very much. So the next header. How do we know what's the next header? So in the Ethernet 2 frame, we have the type field. Now, when the type field has this hexadecimal value, it means we are passing it to IP protocol. So that's the next header. So the next set of instructions for processing are referenced in the type field of the frame header. Remember, really the key function of the frame, the key function of the frame is number 1, to determine the intended physical destination. What is the intended physical destination? How do we do that? Using the MAC address. Number 2, the other function of the frame at layer 2 is to determine the integrity of the frame. So these are the 2 main functions of what we looked at in the previous chapter. Now in this chapter, we're going to see now how we can use another form of addressing. Now this MAC address, we commonly refer to it as a physical address. And why do we do that? Because the MAC address has been encrypted inside the network interface card. So it's called a physical address. Now, on the other hand, The IP address is normally referred to as a logical address. So in a network, devices will have a physical address and a logical address. We call it a logical address because it's just a number and it can change, and it's simply used to send the data from one network to another. Logical address. So in this chapter, we're going to look into IP addressing. Okay, so we begin by looking at the IP header. We begin by looking at the IP header. So generally, the IP header, let me just put it here. IP header, IP header supports, number one, the main functions of the IP header. Routing, number two, what you call fragmentation. Routing is forwarding data between networks, forwarding data beyond its own network, so between networks. That is what we call routing. Then fragmentation is breaking down data into smaller chunks, breaking down of data into manageable blocks. Because most of the time the data is actually too big and it cannot be transmitted the way it is. We have to break it down. So these are the two main functions of the IP header: routing and fragmentation. So in order to achieve routing and fragmentation, this is how the IP header looks like. So the IP header has many fields. They are not so many, just a number. So you must understand each of these fields. Generally, the IP header can be between a minimum of 20 bytes in size, maximum of 60 bytes. So the first field that I'm going to talk about here is the version field. The version field is used to identify the version of IP that we are using. In this particular chapter, we are referring to IPv4. Later on, we're also going to study about IPv6. So when you're using IPv4, then at the version field, we are going to have a value of 4. When you're using IPv6, at the version field here, we're going to have a value of 6, as you're going to see later when we do the practical and we do data capture using Wireshark. The header length is used to specify the length of that IP packet. Then we have what we call the DS field. The DS field is for differentiated service, differentiated service, and field, and it's used for quality of service. Now, generally, later on, we're going to look at something called traffic engineering. So, different packets in the network or different data have different needs, and therefore sometimes they have to be given different priorities, so that in case we have congestion, then ni kama tu venye kwa barabara zetu, we have special cars like ambulances, fire engines that are given greater priorities in certain circumstances. So the differentiated service field is used for that particular purpose. So for example, things like voice data ambayo ni live, video data ambayo ni live, they are given higher priority compared to the other kind of data. So that is achieved through the differentiated service field. Then you have the total length, which also gives the total length of the entire packet. Then we have these three fields here, which I'm going to talk about later. But just to mention, these three fields are the ones that support fragmentation. So I'm going to talk about them in a coming slide. Then we have the time to live. I'm also going to talk about it much later. Then you have the protocol field. Now the protocol field is like the type field in the Ethernet 2 header. The protocol field is used to specify the next protocol to which we are supposed to pass this particular field. Then we have the header checksum. I'm giving you that as a reading assignment. You can go and read and find out what it does. Then most importantly, we have these two fields. So source IP address and destination IP address. Let me just give another example. So you have multimedia University of Kenya. Then you have PO Box 543 MSG 15 543 something and some other number there. So generally you can think of the name here, Multimedia University of Kenya. You can think of this as the physical address, because haitatoka hapo penye iko MMU penye iko hapo Mbagathi, hapo ndio iko, hiyo ni physical address. Then you can think of this address here as the logical address. In fact, in 2010 when we joined MMU, it had a different PO box. They changed it at around 2012 there, in around 2012. So these can change. So that's a logical address. So generally, the IP address is a logical address. It is a logical address. So what we are going to see, but generally, the IP header will have the source IP address and the destination IP address fields. And they're usually assigned to the host. So the host must have a physical address, which is the MAC address, and the logical address, which is the IP address. Okay. Then the last field there is the IP options. When you have other options that needs to be added to that particular data, then they can be specified in this particular field. Things like encryption and so on and so forth. Okay, so let's look at an IP address. So this is what we call an IP address. An IP address is normally written in what we call a dotted decimal format. And if you actually translate it to binary, you will see that it is made up of 32 bits. So each part is actually made up of 8 bits. 8 bits. So this is what you call binary. So when you translate 192 into binary, it's going to give you 11000000. 168 will give you that. 1 will give you 0000000001, like that. Now, so in reading this particular IP address, I'll read something like 192.168.1.1, like that. Now, the other thing that you need to understand is that an IP address will commonly refer, or one part of it will refer to the network, another part of it will refer to a specific host. So if we have a network that has 5 machines, this part here will be the same, but the host address will be different. And this is not very different from our own numbers. So for example, my number is 0729, XXX, XXX. So the very first part identifies the network provider, Safaricom 0729. The other part is now my unique number. So this part is what we're calling the part that identifies the network, and this part is what we're saying the part that identifies the particular host. So IP addresses are also like that. So I hope that is clear. Okay, so here we have two special addresses that are never really used, to assign to end systems. You cannot assign a network address to a host. You cannot also assign a broadcast address to a host. So what are they saying? The upper and the lowermost host address values are reserved. You cannot assign them to a host. Why? Because they are used to define the network. The network address is used to define that network. On the other hand, the broadcast address is used for sending a broadcast packet. When you want to send a packet that everyone will process, you use the broadcast address for that particular network. So if I can just give an example, the very first range in my mobile number should be this number. So that is what we call the network address. What is the last one? The broadcast 0729. I'm not saying that mobile numbers are also used like that, but I'm just giving an example. So the very last number in this numbering range will be 0729 999 9999. Because if we go from here now, we will go to 07. If we add 1 to that, we're going to get 3030, like that. So that very last one is what we call a broadcast address. Now, it is common to identify the network address and the broadcast address because most of the time it will always form a continuous string of zeros in binary, and the broadcast address will most of the time also form a continuous string of ones. So please remember that we do not assign the network address nor the broadcast address to end systems. Okay. So this is the reading assignment that I'm giving you. As I mentioned earlier, these are the three most common numbering formats that are referred to in computer networking: binary, decimal, and hexadecimal. As I said, binary uses zeros and ones. It's called base 2 because it only uses 2 digits. Decimal uses 0 to 9. It's called base 10 because it uses 10 digits. Then this one uses 0 to 9, A to F. Total 16 digits, and therefore it's normally referred to as base 16. But the one that is most important that you need to know how to convert in between is binary to decimal and decimal to binary. I think in my first lesson, in cohort 1, I actually showed them how to do this, and I can edit that video and also share with you. Okay. So this is just a table that can assist you in doing the conversions quite easily. As you saw, as we said, this, if we have 192.168.1.0, if we want, for example, to convert 192 from decimal to binary or the other way around, we know that this part has 8 ones. It's a byte. No, has 8 bits. So that's why here we're being given 8 bits. 8 bits. These are 8 bits. So if you learn how to convert, you're gonna, this is a reading assignment that I'm giving you, so I really don't want to go into it. But if anyone will have a challenge, then let us know so that I can show them. But it's actually quite easy. It's quite easy. It's not something that is very difficult. Okay. So here they're converting this binary representation of the network into decimal. So how to do that? Using the table in the previous slide. They're simply, so this position is called position number 1. This is number 2. This is number 3. This is number 4. This is number 5. This is number 6. This one, sorry, nilianzia 1 badala ya 0. This is 0. Position 1, position 2, 3, 4, 5. Then this is position 6, and this is position 7. So generally, if you want to convert back to this guy from this guy here, you simply multiply 2 raised to the power of the position of that particular number if it's a 1. If it's a 0, it's gonna give you 0. So you simply multiply 2 raised to power 6 plus you add it to 2 raised to power 7, like that. So for this particular instance, this is position 7, this is position 5, this is position 3. So we are gonna add those ones. This is position 0, like that. This is position 0. So you're simply going to do 2 raised to power 0, and we're going to get a 1, like that. If we add this, we're going to get 168. So that's how we do the conversion. Okay, so IP addresses were divided into classes, from class A all the way to class E. What is important to realize is that number 1, only class A to class C can be assigned. Only class A to class C can be assigned to hosts. So before I continue with that, class D is reserved for multicast. You remember we talked of unicast and multicast? So multicast, reserved for multicast. And several protocols use this particular network range, like OSPF, as you're going to see. Then this one was left for experimental, that particular range. So let's go back to class A. So with class A, it is all the way from 1.0.0.0 all the way to 1.6.255.255.255. So I just want you to realize here that we have left out this particular address 0.0.0. It's not included in class A. We're actually starting from 1. We're starting from 1, like that. Now, generally, sometimes if you want to know, if you're given an IP address and you want to know which class it belongs to, you can always check the very first bit, for example. If the first bit is a 0, it belongs to class A. If the first bit is a 10, it belongs to class B. If the first bit, if you convert the first bit, if you convert this first number of that IP address, and the first bit gives you a 0, it is a class A. If it gives you a 10, it is a class B. If it gives you 110, it is a class C. So you might get a question just asking you, tuambie hii IP address ni ya class gani? So you can always convert that first octet into binary, then you look at the first number there. If it's 1110, it is a multicast. If you want to know, it's a multicast. If it's 111, it's for experimental. Now, going to class, so the other thing you need to realize is that in class A, 8 bits define the network, while the rest, 24 bits, define the host. So what does that mean? That means this, that class A network can give us 2 raised to power, where is raised here? 2 raised to power 8 number of networks. So that will give you about, I think, 256, like that. Then, how many hosts will a class A give us? 2 raised to power 24. So I can't remember how much that will give us. I think it's about 2 million and above number of hosts. So that's the other thing you should note there. Okay, let's go to class B. So class B, 16 bits for the network, then 16 bits for the host. Class C, 24 bits for the network, 8 bits for the host. And generally, class C network is used mostly because it gives us a fewer number of hosts and more networks compared to the others. And this is the most ideal situation, because we don't want networks that have so many hosts because of what we call broadcast packets. So we are going to see how broadcast packets are generated when we learn about ARP. Okay, now another IP range that was left out. You see, we are moving from 126, the last one of 126, to 128. So we've also left out the 127. That entire address range has been left out. It's also good to note that at that point. Okay, so that is it about the classes. So always remember which class an IP address actually belongs to. Now, in order to reduce the fast depletion rate of IPv4 addresses, IETF came up with a strategy to make some of those addresses be reusable, and they called them private addresses. So for each of the classes from A to C, they reserved some address range that could be reused in different organizations. So this is a private address. So we have a public address and a private address. A private and public. So within class A, the entire 10.0.0.0 range can be used as a private IP address. So by private, we mean we can use these addresses for our devices in MMU, and KU can also use them. Then we have other special addresses. One of them is called the diagnostic range. Remember the 127 that we had left out is used for troubleshooting. Then the very first address that we had left out, it's called the any network address. So when we learn about routing, you're gonna see how the any network address is used. Then also the very last address in the IP range is never used, is never assigned, cannot be assigned to a particular host. It's called the network broadcast address. Network broadcast address. Okay, so that is it. Okay, so how do hosts really forward data in an IP network? So here we have host A, we have host B, we have host C, and we have host D. Now, host A has been assigned this IP address 192.168.1.1, host C 192.168.1.2, host D, that one, and host B, that one. Now, generally, as we said earlier, this is a class C network, and in the class C network, the first 3 octets are used to identify the network. So here, while the last octet is used for defining the host. So if you check from this diagram, which 2 machines are on the same network? Someone? Which 2 machines? Yes, Nick? Will we be able to hear you?
Yeah, sure.
Yeah, we can hear you loud and clear.
The host A and the host C, they are on the same network.
Host A and C are on the same network.
Yeah, that is .1. And the host B and the host D, they are on the same network.
Exactly.
That is the .2 network.
Very true, very true. Thank you very much. So, as he has rightly observed, by looking at the first 3 octets, host A and host C are on the same network. On the other hand, host B here and host D are on the same network. So, this is how the packet will be processed. So, generally, let me just say this. Generally, host A can be able to communicate with host B. Similarly, or with host C. This one can also communicate to this one, like that. Similarly, these guys can also communicate. So for you to communicate with IP addresses, you must be on the same network. On the other hand, these guys cannot communicate. This one to this one, no. They cannot be able to communicate because they are on different networks. So hosts are naturally aware of the network they are in. And now, in this next slide, we should be able to know how. So we have what we call a subnet mask. The subnet mask. So the subnet mask is commonly used to distinguish between the binary values that represent a network, and the binary values that represent a host. Now, for example, for a class C network, the default subnet mask for a class C IP address is 255.255.255. Now, these consecutive ones mean that this is the part of the IP address that represent the network, while the consecutive zeros mean that these are the parts that represent the host. So in this particular example, we have how many octets? The first octet, the second octet, and the third octet. So what that means is that this part, and this part represents the network. Then only the last octet represents the host. So that is what we call the subnet mask. So the subnet mask is simply used to distinguish which binary values represent a network and which values represent the host. Okay. So these are the default subnet masks for each of those classes. You can just have a look at them. we call them default because you can also have what we call VLSM, variable length subnet mask. Okay, so now let's look at what we are calling here IP address planning. Now, generally, you remember we said that we have something called the network address, which you cannot assign to a host. So how do you find the network address once you're given an IP address and of course you know maybe the default subnet mask? So in order to find the network address, you need to do what we call a logical AND between the IP address and the mask. And you only do the logical AND after converting them to binary. So you convert the IP address to binary, and you also convert the subnet mask to binary. So once you've done that, you can now do a logical AND. So a logical AND goes like this. A 1 and a 1 is a 1. A 1 and a 1 is a 1. 0 and a 1 is a 0. Like that. So we have what we call the truth table. The truth table for a logical AND. So a 1 and a 1 is equals to a 1. A 1 and a 0 is equals to 0. A 0 and a 1 is equals to 0. A 0 and a 0 is equals to 0. So it's only a 1 when all of them are 1s. So that is what we call a logical AND. So we do a logical AND. So once you do a logical AND, bit by bit, you will get a certain binary value. When you convert this binary value into your network, into decimal, then that will be your network address. And this is a common question in the exam. So this will be your network address. So if we convert all these zeros, it will give us 0. If we convert 001 into decimal, we'll get a 1. If we convert this, we'll get that. If we convert this, we'll get 192, like that. So after that, other than the network address, the other thing you need to know is the total number of addresses that it will give you, host address. How do you find the total number of address? You do 2 raised to power n, where n is this consecutive number of zeros in your network address. So in our case, or in your mask, this total number of zeros, actually not in your network address, but in your mask, in your mask. So the total number of consecutive zeros in your mask is what gives you n. So 2 raised to power n will give us 256. And now, to get what we call the valid hosts, we have to subtract 2. Why? Because we have to remove the 2 addresses, the very first one and the very last one. We have to remove the network address and the broadcast address. So the network address in this case is 192.168.1.0. Then the broadcast address. So the broadcast address, how do you get the broadcast address? You can simply add plus 256 minus 1. So that will give you 192.168.1.255. So why plus 256? Because that is the total number of addresses that we get, this 256. But we need to minus 1 because this is also an address. So we are adding 256 hapa mwisho, but we are subtracting 1. So the broadcast address, the very last one in that range, will be 192.168.1.255. So always remember, to get the valid hosts, you must subtract 2 from the total number of hosts addresses. So this is the total number of host addresses. N, as I've said, is the total number of consecutive zeros in your subnet mask. So I hope that is clear. Anyone with a question at this point? Anyone with a question? Okay, so when you get time, I'll want you to convert this. Find the network address, the host addresses, and the valid hosts. So this is an assignment you can do. If you get any challenges, you can communicate in the WhatsApp group so that we support you. Okay. Now, one of the main problems with using the default subnet masks.
Excuse?
Yes.
Can you go back to the previous slide?
This one or this one? Yes, go ahead.
The one with the 172.6.
This one. This one.
I'm okay with it.
Okay. Asante. Okay. So as I was saying, one of the biggest problem with using the default subnet mask is that sometimes they give us unrealistic number of hosts. And that unrealistic or too big number of hosts will cause what we call address wastage. Because most of the time in the enterprise, for example, at Multimedia University, we have small rooms that can handle just a few computers. So we have lab A that can handle a maximum of 30 computers, depending on the seating capacity of that particular room. We have another lab that can handle at most 20 computers. Another lab that can handle at most 10 computers. So how does it lead to address wastage? So when we look at this address 192.168.1.0 with the mask, so 255.255.255.255.0. So the mask sometimes is written in what we call the slash notation. So here when you see /24, it simply means that we have 24 ones that are representing the network, and the remaining now, which is 8, 32 minus 24, are representing the host. So that's why when I see /24, I can just be able to write the other mask notation, 255.255.255.1. So generally, how many hosts will these network give us? So it will give us 2 raised to power n, where n is 8 here. So in total, it will give us 256. 8 because of the 8 number of zeros in the subnet. Then valid hosts will have to subtract 2. So 256 minus 2, we get 254 valid hosts. So you see, this lab only needs 30 computers. So how many addresses are we wasting? A whopping 224. The other lab also, 254 minus 20. We waste almost 234. The other lab, 10. So how many addresses do we waste? 244. So that is address wastage, because we're only going to have 10 machines, 30 machines. So what about all these other addresses? We're going to use them. So to avoid that, we have something called variable length subnet mask. So instead of using the default mask, we use a variable length subnet mask, VLSM. The concept of VLSM is quite easy. Generally in VLSM, we borrow network bits, we borrow host bits, and make them network bits. In the mask, we borrow. So let me just explain how. So here we have a class C address 192.168.1.7. We know that the default mask for a class C is 255.255.255.0. But if we use that default mask, we're going to waste so many addresses. So what do? We borrow. So generally, if you convert this into binary, it will be 111 111 111 dot 111 111 dot 000 000. So that will give us that. These will give us this if we convert it to binary. Now, what we want to do is to borrow this 0, so that now we can change this 0 to a 1. So that now, instead of having this as being /24, we are going to have it as being /25. Why /25? Because we have 25 ones there. We've borrowed 1 0 from the host bit. Now, once we borrow 1 0 like that, it means how many addresses is this guy gonna give us? 2 raised power n. This is gonna be 2 raised power. Our n now is the remaining number of zeros, which is 7, like that. So you see, this guy is gonna give us a fewer number. So the other one was giving us 256. This one will give us, I think, half of 256. That will be 256 divided by 2.
128.
128, exactly. 128. So this one is going to give us a fewer number. What if we also borrow this bit and we make it a network bit? Now we have 2 raised to power this number of zeros. How many are they? They're 5. They're 6, like that. Therefore, you're going to have, I think, 64. You see? So by borrowing host bits and making them network bits, we can be able to conserve IP addresses and therefore reduce the number of IP addresses that we waste within our network. So that is the concept behind variable length subnet mask. Again, even after, so here in this particular example, we've actually borrowed a 0, converted it to a 1. So that's why this subnet mask is 255.255.255.128. So this address will be /25 and not /24, even though clearly it's a class C address. So again, if we want to find the network address, even when we've done VLSM, we simply do the logical AND, then we convert it back. Logical AND between the IP address and the mask. Then we convert it back like that. Then if you want to get the total number of hosts, you do that, 2 raised power n. If you want to get valid hosts, you subtract 2 for the network address and the broadcast address. Okay. So this is another exercise I'm giving you. Ama hata tunaweza fanya, wacha niwaonyeshe hii anyway. So using only the network 192.168.1.0/24, implement VLSM for the given number of hosts in each network segment. So let's do that together. Yeah, good. So we have 192.168.1.0 /24. So what does that mean? 255.255. Oh, no need even to do 255. Let me just 111.111 dot 111. They're supposed to be 8 in each. Dot 111.111 dot 000.000, like that. So now this is what we have. This is our subnet. So 24 bits identify the network, 8 bits represent the host. But if we use this default subnet mask, we are going to waste so many addresses. We already did that calculation. So now we want a 2 raised to power n that will give us should be equal or greater than 30. Really here we're just going backwards. We're just going backwards. So the formula is this. Let me just do the entire formula. 2 raised to power n plus 2. Plus 2 or minus 2? Minus. Plus. So hii tunataka 30 hosts like that. So what really we want is n. What we want is the number of zeros that we need so that the rest can be converted to ones. So I think your formula iko sawa. We're just going backwards from what we did in the previous slide. Okay, so here generally we want our 2 raised to power n should be equal to or greater than
32.
So hapa actually nimeweka 2 wrong.
I think the formula is wrong. It's supposed to 2 raised to power n minus 2.
Yes. It's supposed to be minus 2. The formula is wrong.
No, it should be plus 2 because we are adding the host and the network. No, the network and then broadcast.
Well, let's do this. Let's go back here. Good. So here now we are going backward. So when we go backward, anyway, actually it's supposed to be minus. It's supposed to be 2 raised to power n minus 2 is supposed to be equal to or greater than the number of addresses that we need. Are you getting the point?
Yes.
Yeah. It's supposed to be minus. So it's just supposed to be the same thing. So I think you're correct, Gibran.
Yeah, I think I have a different view.
Yes.
Like for our case, let's take the example of a lab.
Yes.
We need like that host in that lab.
Exactly.
So we must have like the host address, not the network address, and the broadcast address. From my view, I think it should be plus 2.
No, actually, it should be here. It should be minus 2,
Yes.
Because what we need is exactly 30 addresses. Then these 2 ndio zita-identify network na zi-identify broadcast. But we have 30 machines. So 30 machines zinahitaji address. So in total, our 2 raised to power n should be greater than or equal to 32. Umeelewa?
No, I understand.
Exactly. So how do we find n? So our n will be equal to, I think the square root. This is the square root of 32, Sindio?
Yes, the square root.
Yes.
So square root of 32, I think, can be 2 raised to power a half. 32 raised to power half. So what will that give us?
It should be
To give us 5.
5.
5, eh?
Yes.
Okay. So once you get 5, once you get that your n is 5, now you can do 2. What is 2 raised to power 5? It's actually going to give us 32, eh? Okay, so you can see now with this kind of mathematics, really, we are not going to waste any IP address, because if we minus this by 2, because of the host and that, we are going to get exactly what we need. So let's go to the other lab. Hii tufanye ya 10 ama tufanye ya 20. So it should be 2 raised to power n minus 2 should be equal to or greater than tufanye ya 20. So that means hii lab itahitaji 2 raised to power n should be equal to or greater than 22, like that. Then our n, so now we want n. Our n here will be equal to 22 raised to power half. So what will that give us? I think it will still give us 5.
Yeah, it will give us 5.
Yeah, because if we do 2 raised to power 4, it will be 16, eh? So 2 raised to power 5 is 32. So in this particular case, our n will be 5. So 2 raised to power 5 is going to give us 32. 32 minus 2 is going to give us 30. But how many devices do we have in that lab? We have 20. So how many addresses are we going to waste? Just 10. Just 10 addresses compared to 234 that we would have wasted if we would have used the default subnet mask. So when you talk of 5 here, we simply mean that we only need 5 zeros. 1, 2, 3, 4, 5. So the other remaining zeros here, we can comfortably change them to ones. So now this will be plus 3 because we've turned 3 zeros into ones. So it will be /27. So that is what we call variable length subnet mask. I hope that is understood. It's a concept that you can research further so that you can be able to understand better. Then we also have something called the classless interdomain routing. It's normally used especially to summarize routes. So routers, this is a router. A router is used to interconnect networks. And sometimes routers usually have limited storage space. So using classless interdomain routing, several routes can actually be summarized into a single route. Several routes can actually be summarized into a single route. So for example here, all these routes that you're seeing in the local area networks, all those networks can be summarized into the network 10.24.0.0/22. And as you can see for them, they are /24. But once you do classless interdomain routing, it can be advertised as that single network there. So with classless, really, we are not looking at an IP address as being from a particular class. And it's also a form of VLSM. Then we have IP gateways. So you need, so let's look at host B and host A here. Are these two addresses in the same network? They are class C addresses using the default subnet mask. Is host A and host B, are they on the same network? Yes or no?
No.
No. Exactly. So they are on different networks. You can check the first 3 octets, they differ. So they are on different networks. Now, in order to in order to facilitate the intercommunication of host A and host B, who are on different networks, you must introduce what we call a gateway. Most of the time, a gateway is a layer 3 device like a router. So the gateway will have an IP address on that interface that connects that particular network segment or local area network. And that address will have will be on the same network. So as you can see, this address has been assigned to this interface. So they are on the same network. On the other hand, this interface has been assigned this address, same network again as host B. So if host A wants to talk to host B, they'll have to send the packet to this guy, send it to the gateway, then the gateway will deliver it to this guy. So just like the middleman. So in fact, routers are commonly referred to as a gateway routers. But a host can also act as a gateway between networks in a LAN. So in this particular example, in this particular next illustration here, where is it? Sorry. In this illustration here, one of the hosts can act as the gateway and therefore deliver the packet to any of the other hosts that is on a different network. But commonly, routers are used for that particular purpose. So we say that other than routing, the other function of IP header is to do fragmentation. Fragmentation is breaking down the data into manageable blocks so that they can be transmitted over the network. So in order to support fragmentation, the IP header has 3 fields known as the identification flag field, the flags field, and the fragment offset. Now, the identification field is used to distinguish data blocks of traffic flows, which may originate from the same or different host. So for example, ukiwa umefungua browser yako na umefungua Gmail na YouTube. So identification field itakuwa na the same number, packets za YouTube zitakuwa na the same number, packets za Gmail zitakuwa na the same number, packets za WhatsApp zitakuwa na namba ingine tofauti. So hiyo ndio kazi ya identification. Fragments from the same source are given the same identification number. Then we have the flags field. The flag fields is used to determine which of a number of fragments represent the last fragment. So you see here, if we want to send this data, we will have to break it down into manageable chunks. So the first one, the maximum, then the last one ni yenye itakuwa imebaki, but kuna kuanga na maximum size ya fragment. So the flags field will be set to 1. Will be set to 1 in the last fragment. It will be set to 1 so that it can now alert host B that hey, start the reassembly. So reassembly sasa ni kuunganisha hizi data tena. So that's what the flags field is used to do. Then you have the fragment offset. The fragment offset is actually used to specify the value of the first bit following the previous fragment. The value of the first bit following the previous fragment. So what does that mean? Okay. So let's say that this is fragment 1. So let's say fragment 1 imebeba from 1 to 1500, like that. fragment 2 imebeba from 1501 to 3000, like that. Fragment 3 imebeba from 31 to, oh sorry, hapa siko plus 1500 plus 4500, like that, something like that. So kazi ya fragment of set, kazi ya fragment of set ni ku-identify the value of the first bit from the previous one. So kama hii ndio ilikuwa fragment ya kwanza, then the fragment of set will be 1501 for the next fragment. The fragment of set for the other fragment will be 3001. So that is what we call the fragment of set, and it's used for the assembly of data. So those are the three fields that are used for fragmentation of packets. Then we have the time to live header or field, which is here. Time to live is generally a value. That is generated when you're sending a packet, depending on the protocol that you are using to generate that packet. So for example, the default time to live for an IP packet is 255. Now, these routers that are transmitting that particular packet towards its destination, they are normally referred to as hops, a hop. So this is one hop, this is another hop. So every time the packet passes a hop, the TTL value is decremented by 1. The TTL value is decremented by 1. Every time it passes a hop, it is decremented by 1. Now, if any router receives a packet whose TTL value is 0, you receive a packet and the TTL value is 0 after subtracting the 1, then you'll do a number of things. Number 1, you'll check the source. Check the source address. Number 2, send an error message. Let me just call it ICMP error message to that address. Number 3, discard the packet. Discard the packet. So a router, if any router receives a packet whose TTL value is 0, this is what they're going to do. Check the source address. Where is the source address? They simply check this field here. Then send an error message. We're going to look at the ICMP error messages later, like source unreachable. Then don't forward that packet any longer. Just drop it, discard it, delete it. So the purpose of the TTL is to prevent endless looping of IP packets in the IP network. So hakuna venye ati packet itawanda tu kwa network forever, because if this would happen, it will cause congestion. If this was possible, the internet could not work, because we will have so many packets that are just wandering there forever. So in order to avoid that endless looping and wandering of packets in our network and the internet, the TTL value serves that purpose. How? If a router receives a packet and the TTL value is 0, it will do these 3 things, as I've explained. So that is the purpose of the TTL field. Then we have the protocol field. So the protocol field will always identify the next protocol to which we are going to hand over that packet. So that protocol can be a layer 4, that is the transport layer protocol, or it can simply be a layer 3 protocol. Within the network layer, we can be passing this particular packet to ICMP, as we are going to see. So that is what the protocol field is used for. And that is it, ladies and gentlemen. Thank you for your patience. And because we've gone way too much beyond time, I'll just ask if anyone has a question. Then you can take time and go through these questions after we have ended this meeting. But if anyone has a question other than these ones, please feel free to ask. Anyone?
Yes, I have a question on the gateways.
Yes, please.
Are we going to do maybe another lecture on the gateways, or we are just done with the gateways? Like, you may be given like a network, like to determine the gateway of that network. But right now we've just done like very shallow on the gateways.
I think we are going to learn so much about how the gateway actually forwards data, in particular the router, using the routing protocols. So I think we are still going to cover that later.
Okay.
Hapa ni ka intro too.
Okay, thanks.
Anyone else with a question? Okay, thank you very much, ladies and gentlemen.